This video is being recorded by the new Team N lab group, and this is an instructional video for you to be able to perform the Lab 2 yourself. That is a measurement of temperature, pressure, and flow rate. My name is Hannah Cooper.
I'm Katie Hamilton.
I'm Kayla Pilgrim.
And I'm Ricky Glover.
The first experiment to be performed is the thermometer calibration, and the objective of this is to calibrate a thermometer by measuring temperatures in both an ice bath and boiling water.
So for the thermometer calibration procedure, you're going to start by setting up 2 water baths, as you can see in the photo, one with ice and one's going to be a boiling pot of water. You're going to record your surroundings temperature with your thermometer, and then simultaneously someone's going to insert the thermometer into one of the baths and someone else is going to start the timer. The recordings you're going to take on this, Hannah's going to talk about in the next slide. After you take your final temperature recording, you are going to allow the thermometer to return to the temperature of the surroundings and then move on and take the temperature of another bath. Just some things to remember. Remember to take the diameter of the thermometer of the probe of the thermometer, and also just add some variance in the way that you measure these. So don't do all of the hot, don't do all of the cold, and also don't do it in a pattern. So just make sure you randomize the way that you measure the water baths.
The first measurement we're going to want to take, as Katie said, is the diameter of the probe, and this is going to be used for the calculation of the time constant. The next measurements are all displayed in this table here, and the temperature of the surroundings is important to know when the thermometer stabilizes back to room temperature after being taken out of either of the baths. This temperature at which it stabilizes and then the time it took to stabilize are both set to be recorded. And this is done for 5 trials for each bath, and that results in a total of 10 trials performed.
So the final temperature that is recorded, which is that stabilized temperature of either of the baths, is represented by T measure. And for example, if we measured our average temperature to be 98.5 degrees Celsius for the boiling water, the delta T in the equation above would be 1.5 because that's how far away it is from 100, which is the known boiling point of water. And then same for the ice water, if we measured it to be 0.5 degrees Celsius, that delta T would be negative 0.5 degrees Celsius. And then using that, we would make a correlation equation, which is also seen above. And using that equation, we can create a linear correlation graph, which is seen on the right. And that shows the correlation from 0 to 100 degrees Celsius. And then we also took the temperature of the surroundings, and that is used for the equation on the right, which we can use to find the time constant and the temperature. And then we also take that time that's taken can also be used in that equation. And also, like was said, we took the diameter of the probe, and that's used to find the time constant. That equation on the bottom for the volume and the area, we use the sensor that's in the thermometer as a sphere shape, and that diameter can be used to find the volume and the area. And that's just to ensure the safety and when we're taking safety and quality when we're taking those measurements.
The next experiment to be performed is the pressure calibration, and the objective to this one is to read the pressure gauge of a simulated manometer system for pressure calibration.
So for the pressure calibration procedure, we're going to start by setting up the apparatus. So you're going to place the submersible pump in the bottom of your bucket and just ensure that this pump is submerged in water at all times. Then you're going to connect this small tube to this T-fitting, from the pump to the T-fitting, sorry, and then one end of the T-fitting is going to be connected from a small tube again to your pressure gauge. And then the other end, you're going to connect the longest tube that you have and just ensure that the end of this longest tube is placed back into the bucket. Make sure that your pressure gauge is in a readable position, and then just to turn on and off your submersible pump, you just plug it in and unplug it from an outlet. So in order to start this experiment, make sure you set your intake flow on your pump to a minimum, and then turn on the pump by plugging it in and allow the water to flow. Someone is going to then grab the end of that tube that's in the bucket and start to lift it up vertically. As you can see in the photo, one of our team members doing this step. So as you lift it up, you'll get to a point where there's going to be no flow, and that's where you're going to stop. You might get a little bit wet in this portion. And then, so once there's no flow, just measure the height difference between the pressure gauge and the top of the column of water. And then also make sure that you record the pressure reading in this. And then you're gonna change the intake flow to intermediate and then maximum, and repeat this.
To calibrate the pressure gauge, as Katie mentioned, we use 3 different flow rates. So the height is to be recorded each time along with the reading on the pressure gauge. This is repeated for 3 trials at each intake speed, so a total of 9 trials.
So like Hannah said, we are taking the height of the water in the manometer, and that is used in the equation below to find the pressure head. If we times rho GH, with H being the height of the water, we can get the pressure head. And then we also are recording that the pressure gauge, the pressure that's recorded on that gauge, and we can graph that gauge pressure versus the pressure head and create a parabolic model and take that and create a function that models the correlation as it goes, the intake is from minimum to maximum flow.
The final experiment to be performed is the flow measurement, and the objective of this is to calculate flow measurements for a Tetra statuary pump with a fully open valve and a partially open valve.
So for this experiment, you're going to start by setting up your apparatus. So you're going to place that submersible pump at the bottom of the bucket again, and make sure you choose an intake flow, and you're going to stick with this intake flow for the entirety of the experiment. So then you're going to take one short tube and connect it to this valve fitting, and then connect the long tube to the other end of this valve fitting, and then place the end of the long tube in a graduated cylinder. Hannah's going to talk in the next slide about what you're going to record in this. So then you're going to start this, just plug in the pump and begin the flow, and take however many measurements you need. And then you're going to close that valve to partially close, which is going to be more like a 45-degree angle. And repeat this process again with a partially closed valve.
The volume drained out of the tank and the time it took to drain is to be measured 5 times throughout the entire drainage, and this is repeated for both a fully open valve and a partially open valve, as mentioned.
So for this part of the experiment, the flow meter was not technically calibrated like we did for temperature and pressure. Instead, we just conducted a direct measurement of the flow, And the reason we did this is just because we can use this measurement to calibrate a flow meter. So that's what we did for this part. And like Hannah said, we took the volume of the water leaving the tank and the time. And if you graph that volume leaving with against the time, you can get the graph shown to the right over there. And that slope of the two lines for the fully and partially open valves represents the flow rate for each of the valves.
Okay, so applications of experimental design. So we all know that a good experiment begins with an established goal. No experiment is perfect, and they're all going to have something called systemic errors. And these are the type 2 errors that Dr. Lutz went over at lecture. There's no way to really get rid of all these errors, but we can minimize them. And how we do this is with repetition and randomization. So repetition, that's the obvious one. No matter what you're doing in this lab, whether it's taking the height of the manometer or the pressure or the flow calibrations, we're going to do multiple trials. Doing the trials multiple times is going to get us like a more accurate average overall. Randomization, that's also going to help minimize some of those errors. So sometimes in experiments, we might establish accidental biases. So you should randomize some parts of this experiment to get a more accurate average. So for example, when you're taking the height of the manometer, it might be advantageous if you have a different team member measure some of those heights at different trials. You might notice that because of the team member that's been measuring the height, that it's kind of off because of the height of the team members. So by randomizing that, you're going to get a more complete data set. And we get into randomization a little bit more on the next slide. So when you're taking your thermometer calibrations, it's important to randomize those trials. That was kind of discussed earlier, but basically don't just take all the trials of the ice bath and then all the trials of boiling water, and don't just go in between the two, ice boiling. You're gonna wanna make a completely random process of how you do that. It doesn't matter what the process is so long as it's random. Basically, you might establish an accidental bias of, if you measure the hot too many times in a row, you're not really letting your thermometer get back to its ambient temperature, and that's going to throw off some of your results. So make sure you randomize that. Kind of the opposite for your pump settings. Sometimes the lab might have you have your gauge set at 50% or your valve opening just partially opening. You're going to want to make sure that you do all those trials that have the valve setting at a certain setting at once. It would be almost impossible to get those settings the same if you were to alternate them. So basically, any constant that you want to make sure that those are consistent, and then things that you might establish accidental biases on, that's what you randomize. Safety precautions. So the most important thing that you have to remember is to make sure that the pump is completely submerged before you plug it in. The pump does not have an on and off switch. So as soon as you plug it in, it starts pumping water, and it'll break if it's pumping and there's no water covering it. Also, make sure your hands are completely dry when plugging in the pump in and out. What I did is I kept a towel next to me so I could wipe off my hands. Your hands are going to get a little wet just from taking the pump in and out of the bucket. So make sure that they're dry when you're plugging it in and out. Also make sure your outlets are the grounded ones, the 3-prong outlets that are safe to be around water. There's no chemicals in this lab, so just follow normal safety precautions. Obviously, you should be safe around the boiling water. Also, make sure that there's enough water in your pot that you decide to boil it in. If your water gets too low, you'll just be taking the temperature of the hot metal instead of the actual water. So make sure you're careful with that. And that is the end. Thank you so much for watching.